Bob. The recording's in progress. Welcome everyone to this is the third in a series of webinars we're hosting on, or convening rather, on salinity intrusion and salinization in fresh tidal rivers. And in part motivated by how factors like climate change, changes in land use practices, modifications to bathymetry due to dredging and so forth, could alter the distribution of salt in tidal rivers, in particular those which have either drinking water supplies, other water supplies being pulled out of the tidal rivers, and then also impacts on habitats as the salt content in tidal rivers shifts due to upstream or downstream influences. This webinar will focus on the Hudson. We had two previous ones where you can see the websites listed below for the project, and then also for the specific recordings of those webinars. The first was on tidal rivers in the Chesapeake Bay, and the second was on the Delaware River. We plan on continuing the series, moving around the US, but then also expanding to example systems in other parts of the world. The idea to try to sort of look for commonalities and some of the challenges and management strategies to try to mitigate some of these risks to the habitats and the freshwater resources. So the format here will be I'll give a brief introduction, and then we'll have four panelists give different perspectives on the salinity intrusion and salt contamination in the tidal Hudson River, their perspectives on it. And then we'll have a brief period of discussion amongst the panelists, and we'll open it up to questions from the audience. Please feel free to submit questions via the chat at any time, and we'll keep track of those. But then also we'll have an opportunity for people just to raise their hands and ask questions in a free format later on. So with that, I'll go ahead and get started. So as we said, this is focused on the Hudson River. Right now we're looking at the tidal Hudson River near Poughkeepsie, which is at times near the limit of the salinity intrusion of the Hudson River estuary, and we'll come back to why that's important, particularly for the drinking water supplies, which are being extracted from just very close to the bottom of this picture. A little context on the physical setting for the Hudson. It's a tidal river which extends from the mouth near New York City, the Verrazano Narrows, shown there in the lower picture, up to just north of Albany. Its total length of the tidal region is 240 kilometers. And the amplitude of the tides is between 1 and 2 meters, varying with spring neap cycle. And that's much of that tidal amplitude is conveyed all the way up the river. At the upstream end, there are two rivers which join just above the tidal limit, the Mohawk and the Upper Hudson River, and combined, there's a seasonal variability between during the spring freshet period, we have several thousand cubic meters per second during event periods. And then during the summer low flow period, it gets down to into the hundreds of cubic meters per second. And then during low flow drought years, it can get below 100 cubic meters per second. Just note that these are the inputs of the upstream end. There's an additional inputs from lateral tributaries coming in all along the tidal Hudson as well. So what discharge obviously has a big effect on where the salt is that comes in from the ocean. The river discharge is pushing the salt out towards the ocean. So when river discharge is high, the salt is pushed down toward the mouth. For a typical spring freshet here shown for some salinity data for the long channel section moving up the river from the batteries at 0 in New York City. We see the salt gets to about 40-ish kilometers, which corresponds with Piermont and the lower part of Haverstraw or Tappan Zee. Whereas during low discharge periods, the salt can extend much further upstream. This is a summer low flow period when the discharge is about 60 cubic meters per second at the upstream end. And the observations here for, again, sort of scaled with distance along the river from the battery get up to about 110 kilometers, which is near Poughkeepsie, which is important because of the drinking water supplies that are being extracted there at Poughkeepsie. And again, this is an example from August 95. We'll come back to that in a little bit. As I mentioned, Poughkeepsie is the one of 5 municipal water supplies in this part of the river. It's the largest, and collectively they serve more than 100,000 residents. There's also an emergency freshwater drinking water supply for New York City, located about 16 kilometers south of Poughkeepsie, which can provide 100 million gallons per day during low flow drought periods. However, New York City's managed that risk by reducing their demand such that they don't expect to have to use that under the future with the drought conditions they project at the current time. So back to this so Poughkeepsie is obviously it's an important place to keep track of the salt intrusion. So USGS has been monitoring conditions there since the early 90s. And so the top panel, I'm showing river discharge over that period since 1992. And the bottom panel is salinity, the maximum daily salinity measured at Poughkeepsie over that same period. And what we see is that every few years, you get a little spike of salinity where it goes to 1.5 PSU during the summer low flow periods. And so this is something which happens not every year, but it also happens not infrequently. And again, sort of highlighting this 95 case, which we'll come back to. So this salinity intrusion, when it reaches Poughkeepsie, it's a big deal, especially big deal for people like Randy who have to manage the water supplies there. Randy Alstad, who's going to be one of our panelists. But again, it happens on, it's been happening not regularly, but at intervals over a long time. And these are some examples from the popular press showing, in addition to that, those examples going back to the 90s, we had drought periods with salt reaching up to the water intakes in '85. We had an extended drought period in the 1960s, where it was a persistent concern. But then you can go all the way back to the 1913, and there were concerns then about salinity intrusion reaching the water supplies there and affecting the water intakes and requiring additional, an entirely new supply system potentially. So what could be contributing to some of the risks of saltwater intruding from the ocean and reaching the water intakes? Well, one is obviously sea level. Sea level has been increasing over time, as everyone knows. This is the record from the battery, which fortunately have a really long, nice record of conditions there. And you can see that there's a trend of about 3 millimeters per year over the full record. But then if you just look in the last several decades, that rate of sea level rise has increased to something approaching 5 millimeters per year. Another factor is the river discharge. The river, again, is pushing salt out, and so that's a key component to just figuring out where the salt's going to be. What I'm showing here is a time series of river inputs going back to the 19 teens, with a couple time series there. One is the annual mean discharge, and there's a lot of variability. And then the yellow line is the summer mean, the sort of July, August, September period, which is when flow is the minimum and the salinity intrusion is expected to be the maximum. And you can see that, again, there's a lot of variability over time. And there's the suggestion that at least in the recent decades, there's been an increase in both the annual mean and the summer low flow. And so Bob Chambliss, one of our panelists, will also be talking about some of the projections for that and how that might influence salinity intrusion in the future. An additional factor for a highly used urbanized estuary like the Hudson is dredging. And as again, Bob will get into, the water depth is a big factor in determining the transport processes which bring salt into the estuary from the ocean. And so by deepening a system, particularly a system like the Hudson, you increase the salinity intrusion. And there's been a lot of deepening that's happened over the years, over the centuries in the Hudson. And so this is just showing some examples from reconstructed bathymetry from using old charts going back to the 1860s of the natural system, or at least the system at that time. And then a more recent example from after the most recent deepening case. As you can see, like in particular, this lower part of the estuary has deepened quite a lot. You've gone from a ebb tidal delta, which is relatively shallow, to now having a dredge channel, which is 52 feet deep. And this most recent dredging happened in the mid-2000s. So what are the consequences? How is it possible that deepening down near New York City influences the salt up near Poughkeepsie? Well, we can look at this example from 1995. This is just showing a time series zoomed in on the period when there was that little blip of higher salinity in the late summer. The black line is the maximum observed. The gray line is the minimum observed. And then the purple line is if we run a hydrodynamic model using the bathymetry from 1995. And the model does a pretty good job of reproducing that variability, sort of that blip that occurs in late September of increased salinity. If we then just swap into modern bathymetry, we note that there's a big increase in salinity, even though this is an increase of depth down in the harbor, no change up near Poughkeepsie, but a depth down in the harbor of about 5 feet. We see the salinity during this summer low flow period doubles in some cases. So that's certainly one factor which is relevant to not just the Hudson, but potentially to other systems as well. Additional factors that are relevant both here and elsewhere are sort of the salinity of the fresh water that's coming in from upstream. That could be affected by land usage, including road salt application. And so this is just an example from some chloride measurements in wells in a tributary region of the Hudson. And Stuart Finley, who's one of our panelists, will talk more about potential impacts of salinization of waters upstream. And then there's additional sort of operational management factors where if you attended the previous webinar on the Delaware, this is also a factor there, where there are storage reservoirs upstream, which management of those reservoirs could be used to release water and mitigate risk of salinity intrusion during low flow periods, increasing the discharge. But that has opportunity costs to power generation, recreation, and then other water supply usages. And so that's these competing factors of trying to optimize for multiple potential beneficiaries. So with that sort of very high level, broad brush, quick overview, I want to introduce our panelists who will dig in on some of these topics more substantially. First will be Bob Chan, who's a professor at Rutgers University, studies coastal and estuarine physical oceanography. After that will be Stuart Finley, who's a biogeochemist, a senior scientist at emeritus at the Carey Institute. Then we'll have Randy Alstad, who's the water plant administrator at Poughkeepsie, and so he's the person in the world who's perhaps most impacted by this topic. And then we'll have Salme Cook, who is at the USGS, research oceanographer, and she'll talk about some of the work that USGS has been doing, and then will be doing, looking at the future of the risks in this system. So with that, I'll pass it off to Bob.
Okay. Okay, thanks. I'm trying to clean up my window here a little bit so I can see my slides. And I think we are ready. Okay, so yeah, I'm Bob Chan. I'm going to talk about processes that are. My main point is going to talk about like what controls the salt intrusion and maybe the length of the salt front, which we'll be able to find by the 1 PSU isohalide. And as David pointed out, he showed his figure at the bottom at his talk from a drought in 1995, where the 1 PSU isohalide extended up to about almost 110 kilometers, which is right up to the Poughkeepsie intake. And of concern, of course, is how climate, in a future world of elevated sea level rise and maybe changes in river discharge, how we might expect that salt intrusion to change. So sort of key to understanding processes that control salt intrusion are the salt flux. And what are the processes that drive salt flux up the river to start with? And so sort of like the first order process that can drive salt up the river, of course, is this classic two-layer exchange flow shown in the schematic here. where there is a lower layer flow coming in, and upper layer flow going out, and because that lower layer is more salty than the upper layer, this drives a net salt flux upstream, which can be quantified by just the vertical structure of the mean flow times the vertical structure of salinity, which gives an upstream salt flux. And we can characterize that as a dispersive nature, where some kind of dispersion coefficient times the salinity gradient. So those familiar with like Ficking diffusion, it's sort of classic way to describe a flux of material. And we're going to use this to sort of get our understanding of how salt flux will change with sea level rise and river discharge. Of course, more other things can drive salt upriver too, and the tides themselves, despite the fact that they have zero mean velocity over a tidal cycle, because of the correlation between salinity and velocity fluctuation, can drive a mean salt flux. Now, there's a number of mechanisms that can drive tidal salt flux up an estuary, but here's a classic one first proposed by Kubo in '73 and nicely described in a paper by Adrian Garcia that shows how the trapping of water and side channels and coves can produce these regions of fluid that ultimately over tidal cycle will drive a mean salt flux up the estuary. And so both, you can think about that this along channel dispersion of salt, I'll call KX, is a combination of this exchange flow plus a tidal process. Okay, so these two things together can drive salt upstream, and of course, as David pointed out earlier, this is all balanced by a net seaward salt flux associated with the river flow. And so we can then write a sort of a simple salt budget for the estuary, where on the right here, times just the river flow times the salinity, which is driving the salt seaward, times this is cross-sectional area, times this diffusive salt flux that's driving the salt back up estuary. And again, this KX is a sum of the estuarine exchange flux plus the tidal salt flux. And we can simplify this even further by saying that the salinity gradient is going to be the ocean salinity divided by the length of the estuary, so SO over L. And so this nicely gets the thing that we're really interested in here is L, is how far upriver the salt goes. And so, and then once we understand that, then we can see how it will change with sea level rise and river discharge. So in the Hudson, just to give the punchline here, almost all the salt flux, at least particularly in the lower part of the Hudson, is dominated by this exchange flow. And this is some analysis done by Jim Lerzak of some moored observations that show this hot panel shows the lower layer velocity, which is persistently in the estuary. The upper layer velocity was persistently out of the estuary over this 30-day time series or 40-day time series. Similarly, the bottom layer is always saltier than the surface layer, and you can see that the bottom salinity difference has a big spring neap variability, where this is spring tide, very weak, neap tide is highly stratified, but still over the course of this record is a mean salt flux upstream, which is dominated during the neap tide conditions. Okay, and again, you can see this salinity and velocity fluctuations mimic this sort of idealized profiles here, in the sense that we see a vertical structure that's consistent with here. And so with this analysis, Lerzak was able to separate the tidal from the estuarine salt flux, and the basic result, as I said earlier, is that salt flux in the Hudson is dominated by this exchange flow. And of course, these are neap tides where you get these enormous dispersion coefficients over several thousand cubic meters, 7,000 meters squared per second. But anyway, so that's the main point there. So the thing about that is nice is that simplifies our sort of salt flux sort of model, if you would, where we can say that the downstream salt flux by river flow is just balanced by the upstream salt flux associated with this exchange flow. And to sort of, and we can talk about this, we can cast this coefficient, this exchange flow dispersion coefficient, is something we refer to as shear dispersion. And for those, you can, so this exchange, this salt flux up estuary, or this dispersion coefficient, is proportional to the velocity squared, the depth squared divided by the eddy viscosity. And if you want, for those not familiar with shear dispersion, which I'm sure this plan is cool or not, I'll make a little cartoon of it. You can imagine you have a channel like this, got some water column depth at H, it's got a vertical shear in it. And if one were to put like dye in the water, that vertical shear would just tilt the dye over like that. So that's this vertical shear term. And then the mixing, if we mix that up, it would spread it out laterally. And so ultimately, the combination of vertical shear and vertical mixing leads to a long channel dispersion. And so estuarine theory can show that this exchange flow is proportional to the depth squared divided by the tidal current amplitude divided times the salinity gradient. And so we can rearrange all these things with this estimate for the salt gradient, which is again the ocean salinity divided by L, the thing we're after, and we come up with this simple expression here that the salt intrusion length is going to go with the depth squared divided by the tidal current amplitude divided by the river flow to the 1/3 power. The Hudson has been shown to sort of follow this behavior. There's alternative ways we write this, but this is pretty characterized as Hudson today. And so, for example, in this diagram here, what I have here is sort of channel depth going from 8 to 12 meters. And this is river discharge from 100 cubic meters per second to 300 cubic meters per second. So this is sort of like the low flow regime of the Hudson. I think in that drought in 95, flows were down around here. And these contours show the saltwater intrusion. And so you can see during these low flows, you might expect the salt to get up to 112 kilometers up to Poughkeepsie, as we saw. And then as river discharge increases, it gets pushed downstream. Now, of course, if H were to get deeper, if H were to get deeper, we'd expect to go this way, and therefore salt would extend way beyond Poughkeepsie up to 130 kilometers. But also, there's some climate projections I'll talk about later, or Dave also showed that the river discharge might increase, or the minimum, if river discharge increases, it could mitigate that in fact. So in this example here, if we had a sea level rise of here, but an increase in river flow here, saltwater intrusion would not change at all. And so you could look at this is the length of salt intrusion. If I neglect changes in the tidal current amplitude, which I don't need to do, but just for expediency, I will for now, one could say the time rate of change of the salt intrusion is going to scale like these two terms. And so this term here is the changing depth of the water column. It's going to cause the salt water to go further upstream, where this is the changing river flow. If this increases, it's going to cause the salt front to advance. And so when this dominates, salt goes up estuary. When this dominates, the salt goes down estuary. And the ratio of those two is this. So it's just H over 6 times Q times the time rate of change of the river flow divided by the time rate of change of the water depth. And so when this thing is greater than 1, salt retreats. When it's less than 1, salt advances. And so just to get the numbers on dQdt, Dave had shown this figure essentially, but I just added a couple extra lines to it. I have a line here from 1960 to today and one from 1980 to today. And there's a variability in river discharge. This is again a low flow during the dry months. The annual mean for this time period, July 15th to October 1, and there was a 1.6 meter cube per second per year since 1960. That's been elevated to 2.5 meter cube per second per year since 1980. There was this big, famous drought in the 60s, followed by this big wet period in the 70s, and so these trends may involve some obviously climate change, but also could be sort of more decadal scale variability. But those are numbers that we get, and we get something like, if you want to, about 1% increase per year in river discharge according to those lines. Sea level rise, I took a little narrower window than Dave had, and I got 5 millimeters per year. And this has been accelerating in Hudson in recent years. And so, but just a quick comment about sea level rise is that if there is the water column in 2000, if you had a sea level rise by 2050, you might expect the water column to increase. But of course, that's not the only story. There's also sediment deposition, and so the bottom can actually be, increase over time. I mean, 50 years is a long time for when you start thinking about deposition. And in fact, a couple of papers that Dave Ralston led, if you read them together, suggests that there may be a sufficient sediment supply for the Hudson to keep up with rates of up to 10 millimeters per year. So if we're below that, it's going to get, this would suggest it's not going to get any deeper, but if sea level rise go above a centimeter per year, then we probably won't be able to keep up with sea level rise. And this is consistent with an older paper by John Woodruff that that found that on sediment core data, the deposition and erosional processes maintain an equilibrium condition on 100-year timescales. So other projections are available too. This is from Climate Change in Hudson Valley, from Cornell, and they have a lower projection of changes in precipitation, which is not river discharge, but if we just if they're proportional, this is about half of what we saw in the river. I know these are their sea level rise projections, and they tend to be from a really low side, which is 2.5 millimeters per year, which we've already blown past, up to 1.5 millimeters per year. This is by 2050. This is from 2014. Hopefully there's some updates coming soon, if not already, and other projections, but these are kind of key. And so if you were to look at this simple salt intrusion parameter that I put here, you can see if this is the rate of increase in river discharge, and this is a sea level rise, the Cornell projections, because of their elevated sea level, because of the higher end of the sea level rise, because they're projecting towards 2050, a place that 30 years from now or 27 years from now, we'd expect salt to advance. The time rate of changes of river discharge that we saw in the river discharge puts them here, and at the current sea level rise rate of about 5 millimeters per year would suggest the salt retreats. Now, again, this figure does not consider sediment accumulation, which would push this line way up here, suggesting that even up in this corner here, we may be able to have salt retreat. Or, of course, it doesn't include future dredging, which would be certainly push this line in this direction. So just to end that, I want to say that the main points here is the effects of the sea level rise on increased saline intrusion in the Hudson is likely to be partially mitigated by increases in river flows and sediment deposition. Predicting salt intrusions in the future would benefit from a climate projections that include changes in seasonal precipitation patterns. And I say that because we're really interested in the low flow period. And even though maybe river flows go up, but maybe in the summer times they go up more, or maybe they go up less. And that's going to really be influential on what the concerns at Poughkeepsie. And then a final caveat of a lot of this work is that while the Hudson is a very well studied estuary, much of the work is characterized in the mesohaline reach further downstream, and future work should study the oligohaline reach of the river. Okay, thank you.
Thanks, Bob. Our next speaker is Stuart Finley. He's going to talk about some of the upstream influences and then also the impacts on ecosystems.
Thanks, Dave. And before I get into slides, I just want to thank the organizers for putting this together and for everyone coming to listen. This whole salinity intrusion thing is a really big deal, both from human uses and, as I'll show you, could very well be from an ecological point of view as well. And the sooner we get out in front of this from a management understanding point of view, the better off we're going to be. So that'd be one of my take-home messages. We're very fortunate that we're getting started worrying about this. So let me share my screen. Blown up here. Okay, so I want to talk about three basic topics here. And first, very quickly, I'll talk about the salt input from the tributaries, since David brought that up. And we do have good data on various tributaries and how much they contribute to this issue. And then I want to talk about four aspects of the ecology. And to me, it's useful to break these up into things that cannot move, or at least not move very quickly. And so as the salt comes upriver, they can't run away and hide, so to speak. Versus some other things that have a couple different ways of moving around in response to the front. Obviously, the fishes are highly mobile and the phytoplankton somewhat less so. And they may be affected by this vertically, not horizontally. So I'll go through these as described. So here's some data from it's the same watershed David talked about. These are chloride concentrations in various tributaries of the Fishkill Creek, which is one of the bigger tributaries above the salt front, usual salt front location, which is sort of Newburgh, give or take. And there are a couple messages here. The most striking thing is that these are summertime concentrations, and it's quite typical in the streams we've looked at in the mid-Hudson that the summertime concentrations are as high, if not higher, than wintertime. So the salt's getting hung up in shallow groundwater, it appears, and when base flow sort of kicks in, that saltier stored water is contributing a lot to loads out of these systems. So the concentrations are high. The good news part from a sort of worrying about salt point of view is that the flows are pretty low in the late summer, early fall time. So we could do sort of back of the envelopes of how much is this contributing relative to the tidal advection that Bob just got finished talking about. My guess is it's going to be small because these are relatively small tributaries. But again, we have the information to do it and see just how big a deal this might be. Locally, from a drinking water point of view, it's a big deal. The 100 milligrams chloride that I mentioned before, sort of halfway up my y-axis here, that's a limit for people on very restricted salt diets. And so that number does matter something to a segment of the population. So that's it for the tribs. Maybe more if my slides won't advance. There we go. So the first habitat that I want to talk about in the immobile, can't run away and hide class, is the submerged aquatic vegetation. And this is primarily Vallisneria americana. It's called water celery. It's called a lot of things. It's incorrectly called eelgrass in some cases, but it's not. And there's a whole body of research that shows it's extremely valuable habitat. It's used extensively by small fishes that are spawned within the river. It contributes to dissolved oxygen in the Hudson. It's occasionally important as a food resource, but that's probably not the major thing. It's the habitat, the physical structure that it provides that's the key thing. At some level, it's sensitive to salt intrusion. If you look in around Piermont, Haverstraw Bay, there's very little of this habitat. That could be due to salt, could also be due to turbidity, because the river's more turbid down there, and these plants are strongly light limited. But we know in other systems that they are in fact affected by salt at some point. We don't know the exact level for the Hudson, but it's something we could reconstruct either from data from other systems or by looking at current distributions and the salt that occurs at those locations. There's not another species so what's likely to happen if the river gets saltier is this plant is going to disappear from the southern end of its distribution. It's not going to be tolerant to those salt levels. And exactly what those levels are, we're still waiting, of course, to find out. But we're probably going to lose the southern end, and there's not another plant sort of poised to fill in that gap. So we're going to lose habitat, and there's not very much of it right now. So we're pretty concerned about loss of this plant. It happened before when Irene came through, and we essentially lost 90% of it river wide, and it took something like 8 years to come back. And so even an episodic salt intrusion could cause a big problem for this plant, and recovery would be slow. So that's the first habitat that can't move. And here's the second one. This is a photo of one of the tidal marshes of the Hudson. And there's a very striking zonation here in the foreground. It's about 60 centimeters lower than what's in the background. And the plants in the foreground are inundated at high tide. The plants in the background are only partially inundated at high tide. The plants in the background are primarily responsible for many of the habitat values here. And there's physical structure. These are much more robust, upright plants. They're very important in nutrient removal, both through direct assimilation and through denitrification. And there's a fair amount of carbon sequestration that's happening in that higher marsh zone. Probably the biggest thing for this particular system, these marshes, is the actual inundation regime, because we know that some of these are going to be subject to basically drowning is what it comes down to, unless, as was already mentioned, there's sufficient sediment supply to keep up vertically as sea level rises. So we're very worried about inundation, period, whether it's salty or not. When you add the salt in, there are a couple of things that happen. So the high marsh plants, there are a couple of plants in the area already that can tolerate some salt, Spartina being the most obvious, and Phragmites is actually more salt tolerant than the cattail you see in this particular photo. And so there are some plants that are sort of ready to move in if salt conditions become unsuitable for the cattail. So that's true for the high marsh. For the low marsh species, there really aren't a set of plants salt tolerant ready to take over this habitat if the current residents can't take it anymore. And so what's going to happen is you're going to wind up, if the salt regime gets severe enough from these plants' perspective, you're going to wind up with mud flats instead of vegetated marsh. And for habitat reasons and carbon removal reasons, that's probably not a good thing from sort of the whole system functioning. So my guess is what's going to happen with these things is we're going to retain the total area of marsh, but the composition, the vegetative composition, is going to change quite a bit with the loss, I think almost complete loss of these lower marsh plants and a replacement of the high marsh plants with something else. We anticipate some fairly significant changes as this happens. And currently in marshes of the Hudson, you can see this sort of gradient going from up here, where I'm near Poughkeepsie, in the Allegheny part, all the way down to Piermont Marsh and further south, which are currently fairly brackish already and have different attributes. Okay, some things that can move, and the most significant are the fishes. There are a whole variety of fishes that move up into the Hudson to spawn. The striped bass and the shad are probably best known. Their activities are in the spring, when it's likely that salt is not going to be much of an issue for them once they leave the ocean. So that's not such a big deal. But in the summer and fall, there are a variety of marine species that come up into the lower Hudson. And whether it's to avoid predators or have an opportunity to feed on these potentially naive freshwater fishes, and the young of the year, recognize that all that spawning activity by the stripers and shad and others upriver in the spring results in young of the year that have to head back south out towards the ocean as winter approaches. And so the way I look at it is these young fishes have to run this gauntlet of predators. And if the marine species can move further, come in sooner, stay longer, it just makes that gauntlet all the more daunting. And many of the fishes that are spawning up here in the Hudson don't need any more trouble. Shad have plenty of problems as it is. The stock's in terrible condition, and so they don't need an additional stress. And this would be worth looking at if we determine that the salt regime is going to be really quite different. The last thing I want to talk about is something that moves, although it doesn't necessarily move by itself. And that is the phytoplankton. So right now, there are obviously plenty of phytoplankton in the river, and it is rare that we see blooms of either green algae or, more troublesome from a drinking water point of view, the blue-green bacteria. We do occasionally see blooms, not very often. And the Hudson is loaded with nutrients. And so what's been saving our proverbial bacon here is that the single-celled phytoplankton, again, either the algae or the cyanobacteria, they get mixed down into the water column. So on average, the water column is about 11 meters deep, and with complete mixing top to bottom. And so what happens is that even on a sunny day, at best, these cells are in the light for about 10% of that, right? So they're strongly light limited. And one of the potential issues with increased salinity intrusion, and this showed up in some of the haloclines that David showed earlier, is you could get a little bit of transient stratification that might be sufficient to keep these cells up in the photic zone where they're getting more light for longer periods of day. And that stratification may last a few tidal cycles, it may be several days. But if it really lets these things sit up there and get all the light they would like, and they've already got all the nutrients they need, it may trigger more blooms, more frequent blooms, and blooms that have a greater extent. So there have been little hints that this might have happened in the past in certain regions, but increased salinization gives you another mechanism to generate some vertical structure in the water column, potentially allowing these things to bask in the sunlight, so to speak. So the good news here, I think there are two good news things. One is that we haven't seen huge changes in salinity yet because of this balance that Bob talked about between freshwater flow and rising sea levels. And we've got a good handle on what's already out there and how it might be affected. So when it comes for looking for changes and the possibility of mitigating some of these changes, we would be in a good position to say, here's what we might lose, here's how we might do something about that. And so I'm going to leave it at that. And again, just thanks everybody for participating and setting all this up. And I will stop sharing.
Thanks, Stuart. Okay, next up is Randy Alstad, and we'll speak from the perspective of Poughkeepsie Water Department Management Strategies.
Hello there. I think I'm up, right? Okay. So my topic is the impact of salt front to Poughkeepsie. I'm the water plant manager for the Poughkeepsie's water treatment facility. As you said, we serve around 100,000 people. And first slide, we go. Okay, so Poughkeepsie is an interesting facility. It was started in 1872. We were talking before the presentation that Poughkeepsie was known as a sickly city because there was a lot of different typhoid. We used to measure typhoid here. And in 1872 is when they had the first filtration plant built in the United States. So currently we average about 11 million gallons, and we're at 77.2 miles up from the battery. So you can see the little red dot on the screen. It's pretty close to where we are. Why is salt front a concern? Well, a low sodium diet is 2,000 milligrams per day. And as Stuart said, a severely restricted sodium diet permits 1,000 milligrams of sodium per day. So it's a concern for people that are on low sodium diets. Salt front, as we were talked about earlier, was the location where the chloride concentration is 100 milligrams per liter, which equates to a conductivity of roughly 510 microsiemens per centimeter. State requirement in New York requires that at 20 milligrams per liter, the customers are notified. We're typically in the plant is between 15 and 25. This year we were over 50 milligrams per liter sodium. State MCL chloride at 250 milligrams per liter. Back in 2004, we had 230 milligrams per liter. So it is a concern. This chart seems to be one you saw, but this is what we're looking for. Trying to know where the salt front is easy to monitor by conductivity. So we have conductivity, and we have conductivity data. We have chloride data, and we have sodium data. So this is a graph that's showing whereabouts it is. Here's the 20 milligrams per liter, and you can see about 320 conductivity. And then when you go up to 100, this would be the chloride line. The 100, you're talking way up 500. So, yep. Okay. This chart you can see, which is similar to the ones you've already seen, but it shows that above the line here is Poughkeepsie. You can see we hit a salt front pretty much every 3 to 4 years, sometimes more or less severe, but it'll go over every couple of years. The big key for us is the flow in the Hudson. This is a nice graph. It shows right to where the point of the salt front is based upon the flow from Green Island, which is a measurement in the upper part of the Hudson River. Again, this is real data, not the data we've shown from USGS, but this is our data. So you can see the 510 conductivity, and this last 2 years, it's been in 2020 and 2022, we were over that. So we had the salt front here. What's going to happen next? We don't know. The salt front of DEC is going to be putting out another $500,000 to do some more modeling in the river, which is a good sign. One of the talks has been if we somehow could connect to New York City water. It's a long ways away, but it's a possibility. The problem with Poughkeepsie is we only are relying on the Hudson River. We don't have a backup. And so it's a very sensitive location for us. And also there's a potential for treatment if it got to the point where we had to remove the sodium. So that's what I got. I hope that which is what you need like to hear.
That's great. Thanks, Randy. So next up is Salome Cook from USGS, and she's going to talk some more about what we're going to do, or what they're going to do, I should say.
Let's do this. All right. Let's go to presentation. Where am I? Presenter mode, where am I? Slideshow. Okay. Can everyone see my slide? Is it good? Is it presenter mode?
We're seeing the presenter mode. So
okay, so that's not using slideshow. Okay.
Perfect.
Great. All right, everyone. My name is Salome Cook, and I am a hydrologist and oceanographer at the USGS. And today I'm going to talk about some of the work USGS has been involved in and will be involved with in salinity intrusion in the Hudson River. Okay, so some background in the USGS. We are the sole science agency within the Department of the Interior. We are the largest water, earth, and biological science civilian mapping agency. And so our mission is to monitor, analyze, and predict current and sorry, did that just escape? Okay. So we want to monitor, analyze, and predict current and evolving dynamics, and we want to lead the nation in the 21st century integrated research. So this sort of salinity intrusion study fits right into our wheelhouse. And so I just wanted to cover or sort of reiterate what the salt front is in the Hudson River. As has been said a couple times, it's a chloride concentration of 100 milligrams of chloride per liter, which is about a specific conductance of 510 microsiemens per centimeter, or a PSU of about 0.25. Right in the state maximum contaminant level is about 250 milligrams of chloride per liter. And so in order to get chloride concentrations, it requires sort of lab equipment. So that's why Randy sort of talked about using specific conductance as a proxy for chloride. So we can measure specific conductance in the field. We just need sort of a relationship between specific conductance and chloride. In the past, the USGS has created this relationship you see on the right. And we've reported the location of the salt front using high slack tide values. And so that past study was by DeVries and Weiss, and I think it was published in 2001. This was a one-dimensional modeling study using a dynamic flow model and in conjunction with a 1D solute transport model. It covered 132 miles of the Hudson River estuary from Hastings on the Hudson to Troy. And you can see that within this study, and these sites are still available, I believe most of them are, the black triangles are the locations of those specific conductance gauges. And so that's how, using a regression analysis, the study sort of predicted the location of the salt front. And this is sort of what the outcome of that study was. So daily salt front predictions using the regression model from October 1991 to 2015. This bottom time series is the location of the salt front. Over that time period, you've seen it in a couple different forms from the other speakers today. And so what came out of that study was a sort of spatial location of where the salt front was within the estuary and the reported salt front location, but has since not been reported or predicted. So then I'm going to start talking about some of our future current and future work. But again, this was just a 1D study, and so there have been plenty of three-dimensional modeling studies of salinity in the Hudson. Some of that is shown here. So there's some references for past USGS studies and related studies using this modeling system, which is COAST. So COAST is a coupled ocean atmospheric wave and sediment transport model. So it's a three-dimensional model, and it can couple a bunch of different sort of modules together. You've got ocean, wave, sediment transport. The capabilities of a 3D model are that you can look at sediment transport, mixing and salinity intrusion. This is what I'll sort of talk about in terms of what the USGS's future work will be. You can look at wave impacts on marsh. You can couple larger models, so hurricanes across the Mid-Atlantic Bight to the estuary itself, and look at residence times of different things in the estuary. And so our proposed USGS river salt front study, the objectives of this study are to identify that salt front location and describe the drivers of salinity intrusion in general, of which you've heard a lot today from both Bob and Dave, and identify the magnitude, duration, and timing of that intrusion under past, present, and future conditions. And this is including changes in discharge and sea level rise. And so the domain of this study will include offshore conditions, probably a little bit farther offshore than what's shown here, and include and go all the way up to Troy, New York, and perhaps maybe even have an inset model where we include the salt transition zone, which tends to be between Hastings on the Hudson and between West Point and Poughkeepsie, but probably include a little bit north of Poughkeepsie, where this drinking water plant is here. So the main drivers that we're focused on are river discharge and tides. We saw the spring neap cycle affecting salt intrusion. Meteorological events, that could be increased precipitation effects on the discharge, or it could be, offshore subtidal or sort of storm surge conditions that lead to a salinity intrusion event, or bathymetry, which you've heard about, which both in terms of dredging and sedimentation could affect the location and movement of the salt front. And so the scenarios that we are focused on are, and we're using COAST, which is the 3D model I showed before. So it's been used widely, it's been vetted in the Hudson River. And so we're going to sort of take this model that's been used and apply it to answer this, these questions about salinity intrusion. And so there's the scenarios we're covering are to sort of get at both of those main drivers that have been discussed, which is river discharge and coastal water levels. And so coastal water levels, include sea level rise, tides. River discharge includes sort of mean discharge plus maybe any larger events. So the reason we're interested in covering a large range of river discharge conditions is because you've seen the graphs earlier today that the Northeast has seen a 70% increase in rainfall and increase in heavy precipitation events. And projections of these events, projections are that these events will continue to increase, but they're mostly in the winter and spring. As Bob suggested, even though they might be bigger in the spring, that doesn't necessarily suggest that there'll be bigger precipitation events in the summer and fall, which is where we really worry about the salinity intrusion. So we're sort of going to look at both projections in precipitation and discharge and, past observations of discharge and come up with sort of a probability space of discharge conditions. And then also run sea level rise scenarios based on DEC approved projections, which comes from the this part 790 of the New York, I forget what the acronym stands for, but right in the Northeast, we know that sea level rise the rate is changing and in fact increasing. So from sort of, this kind of chart will pull out some sea level rise scenarios. So cover sort of the probability space of future discharge and sea level rise and determine the effects on the salt front location. And so that's the proposed work. What could, the outcomes of a study like this look like? Well, It could look like, maps of the spatial and temporal distribution of salinity. So that could be different regions of the Hudson having, showing what the distribution of salinity is. It could look like, the outcome of the last USGS 1D study where we have the location of the salt front, both in sort of style or over time. And then, getting at what Stuart talked about, maybe the number of days the salt front stays in each reach of the estuary could impact, if you split the estuary up into reaches and have, days the salt front or the salt concentration or the chloride concentration is above a certain value, that might help you determine, how some of these natural resources might shift in the future. And so that's sort of an overview of our past and future work. And that's all I have. So I'm happy to take any questions.
Great, thanks, Alma. Okay, well, so that's all the prepared presentations, and I guess I would go ahead and open up the floor to participants to raise their hands or put in questions, and then encourage the panel members. Ming Lee is one of the organizers of the overall project to try to bring together these webinars, and so he's going to join us as well on the panel. But yeah, I guess sort of the aim is to field any questions from the audience, discuss any of these more topics in greater detail, and just keep the conversation going. So Bob, why don't you kick it off?
Yeah, Selma, that was great talk, and I would like to hear, do you have any insights into you talked about the more extended droughts in the summer? Are they calling for actually decreasing river discharge in the summer in the future, or because one thing, it seems like there's like these incredible precipitation events in the summer too, but I guess
I think that's a really great question. And I think what I've read is that there's not necessarily a trend of more or less in the summer, but if there was sort of a really big drought in the summer, or even maybe a moderate drought. So that's why I think we're taking the sort of tactic of doing sort of like a probability space, like maybe like a drought, mid and high. Another project I'm on has looked at future projections of discharge in the Northeast in general. And we try to match the 1960s drought to like a 2050s drought with sea level rise. And they do, the projections are that they could occur. But I don't know in terms of, is it going to be more or less like the variability of discharge in the summer? I don't know.
Can I ask a second question? That is, maybe Dave could also chime in on this too, is how well do we have an understanding of how, suppose it's a 20% increase in sediment in river discharge, and it was more associated with heavy precipitation, intense rainfalls, presumably that would increase sediment flux to the river too. And does anybody, and of course it's all complicated because there's land use changes and all that, and so getting a grappling with the change in sediment supplies. Anybody have any thoughts about that?
Yeah, I think at the conceptual level, you're absolutely right. Most of the sediment load goes as a higher power of the discharge, and so you increase the discharge a little bit, you increase the sediment load a lot. And so I think we certainly see that with extreme events like Irene, where many years of sediment came in just a couple days. There's also shifting land use patterns. A lot of the Hudson was pretty built out, or sort of developed. Forests were cut down, farms were put in hundreds of years ago. And so then there's a question of sort of how that's continuing to change and how that land use patterns might influence the sediment supply. But I think you're absolutely right that is a question. Again, I would expect with more extreme storms, if you have more variability, that would lead to greater sediment supply than just increasing the mean discharge.
There's some questions in the QA. There's one from Alice Horner Davin, and for Stuart. Are marsh considered important in flood protection in the Hudson River? If so, how do the changes you're expecting likely to impact that benefit? Stuart, you're muted.
Yeah, so thanks for the question. I showed the picture of the high marsh and again, those very dense and robust plants. They've been shown through some storm modeling to be very good at protecting adjacent human communities from debris and surge, not necessarily so much for just inundation, but it does dampen down the wave action quite a lot. And a fair amount of the damage that occurs is by just material getting pushed around by the storm surge and waves. And it does help with that. So for inundation, not really. It doesn't, dampen out the water level increase, but it provides a pretty good physical barrier against some of the damage during a storm surge. And there's a published paper on that I would have to dig up. I don't have it on top of my head.
Stuart, just follow on that question. We know that in that transition zone from salt to fresh water, it's a very productive, marsh system there. As the salt front move further inland, how does it going to change that, freshwater marshes? And you show one species that how it possibly could disappear.
Right.
But what about other species that, what potential impact on that?
Again, from a plant point of view, there aren't other species sort of poised to come in and occupy what is likely to be bare habitat. You can get algal, benthic algae occupying those mud flats, but not other vascular plants. There are effects of salt on nitrogen cycling, and these have been shown in a number of estuaries up and down. And long story short, as the system gets saltier, transitions from freshwater to saltwater, they become less of a nitrogen sink. So they're more likely to leak nitrogen. Instead of acting like a sponge, they act like a source. And so exactly, the dose and duration that's required to make that happen seems to be system specific, but it is what's expected to happen. Also, salt affects whether or not there's likely methane emissions from these wetlands. So there are a number of biogeochemical implications of having saltier water on top of what used to be a freshwater sediment.
There's a question in the chat about the Q to the -1/3 power law that Bob showed as far as the salinity intrusion and the extent to which that was derived analytically or through data fitting, and if there's a reference for that. Bob, do you want to take that?
Yeah, well, it's both analytical. I mean, if you have a prismatic, if you have a uniform channel, straight, same depth everywhere, same width, and mixing is the same, you get Q to -1/3. But there's been some debate in the literature about that because some estuaries are shown such as that are bad actors, like the Delaware and San Francisco Bay was being Q to -1/7. But there's this Dave Ralston has a really nice paper on showing how geometry and river discharge influence salt intrusion, and in the Hudson he does show Q to -1/3, and I'll be happy to send you that paper, or if since Dave's so busy running this webinar, so
I'll send you a nice bottle of wine for that.
thanks. All right, I'll send you 3 papers then.
So I had a question for Randy. As a water user, we've seen in other systems that there's not just a drinking water user community, but also potentially industrial water users or agricultural water users. Are you aware of that being a concern in the Hudson, either near you or in other parts of the Hudson?
No, I'm not aware of any.
And then as far as like the management strategies for the risks that you face, what do you see as sort of like the most likely scenario for how to try to minimize the risk going forward, or actually maybe multiple paths are keeping open?
I think for us, the salt front really happens infrequently and it doesn't last that long. So as long as customers are advised, they can pretty much be okay with it. We can do some pumping around the tide to try to minimize how much we get in, but that's pretty much what we can do other than live with it. I know when we had in 2004, people in New York City were calling up and say, why am I feeding people salt? So it can get blown out of proportion, but it does happen.
And I think that Alex has a question of Sami. do you expect offshore coastal meteorological band variation in water level to impact salt intrusion events, or are the impact too far upstream?
I don't actually know the answer to that. I think it can affect the salt front movement, but whether it'll affect Poughkeepsie, I don't actually know because I haven't read any papers that talk about or maybe if I have, I can't remember at the moment if like an offshore storm will, I mean, I think it certainly could lead to higher intrusion because you have higher water levels, right? It changes the depth and it increases salt. I don't know if it's gone all the way up to Poughkeepsie. Have you noticed any storm-based, Randy, event-based intrusion?
When Sandy went in, the water level went to really high.
Right,
I don't really recall measuring salinity at that time, but
right,
that was quite a lot of water.
I
right.
also, I think there's an example of it also in a paper. Jim Lerzak has this paper on time dependency.
Right.
And there's like, I was really perplexed by this figure because there's this, it's pretty high river flow, but there's this big salt intrusion. It was a storm, and if you read the paper, there was a storm that did it. It didn't go to Poughkeepsie, I don't think, but it went pretty far upstream.
Right, yeah. So it could have like sort of the natural resources effects, maybe not the drinking water effects, but it might affect other areas.
And one good question too, does those storms, do they just bring salt up and bring them back down, or is there some residual dispersion associated with those?
Yeah, I'm curious about that and sort of the interaction of a lot of water coming up and then, those sort of like latent up the tributaries or bathymetric effects that could lead to salt staying in an area.
Stuart, do you want to ask a question? Raise a topic.
I do. This is for the physical oceanographers, and this idea of the salt coming up the deeper parts, and obviously in the upper, mid and upper Hudson, we've got the navigation channel, which is 10 meters, and then most of the rest of the river is actually quite shallow. So listening to you folks, I've got this notion of sort of a tongue of salt water coming up the navigation channel. And then I start to wonder what's going to move it laterally into the shallower parts. Can you get something like a transverse seiche or something like that? How would it, sort of slosh up onto the shoulders, if you will, of the bathymetry? Or is that not something to be thinking about?
Hey, you want to take that, or
Go ahead, Bob.
Well, yeah, I mean, there's a lot of processes that drive lateral flows in these systems. One is like during a flood tide, you tend to get the boundary layer, it fills up the main channel, and then and that produces a cross channel density gradient, which then it'll just like gravitational adjust over the side. There's also, even though the river is narrow, some effects of the Earth's rotation can influence it, but also more importantly, flow curvature. Whenever there's flow curvature, and if you look at any channel, you may think it's straight, but if you look carefully, there's always wiggles and bends, and every time it wiggles, you'll get water squirting up one side. So there's a number of mechanisms that can definitely put stuff on this flanks. But just as a comment, in general, like in a lot of these systems, you do see like there's a paper by Rocky Garden in Delaware that shows some really that the channel, much of the salt flux is dominated in the channel, and of course Delaware is very different because it's got big wide flanks and a narrow channel. And so even though deepening the channel may only increase the cross-section area by a little bit because it's so wide, since all salt flux is happening in the channel, it could have outsized impact.
I think there's a question in the QA by Xiaoyang Wei, to Dave. Dave mentioned potential impact of rose salt on salinity level in river flow. Do you think that if groundwater saline intrusion is likely to strongly affect estuarine salt transport process and salt intrusion length?
Yeah, that's a good question. We brought that up just because we have seen in other systems that particularly this increasing salinities in the tributaries and the rivers feeding in. Like for example, with the Delaware at Trenton, there's been a steady increase in the chloride level in that sort of fresh water. Stuart mentioned that is occurring sort of at the local level, both in the groundwater, but then also in the tributaries, in some of the side tributaries of the Hudson. It seems to be less of a concern in the main river flow, the main volumetric input into the Hudson, which is the Mohawk and the Upper Hudson. Those are particularly the Upper Hudson's coming from a relatively undeveloped watershed, and then the Mohawk's a more sort of agriculturally oriented watershed rather than being highly urbanized. And so it seems like at this point anyway that at least at the scale of the estuary itself of the Tidal River, it may not be a leading order issue in this system, but certainly it could be a factor locally, whether you're drawing from groundwater wells or from a local tributary, as far as within some of the smaller side tributaries of the system. And I honestly don't have any idea what the groundwater flux to the Hudson is within the Hudson Valley. I would imagine it's not big compared to the freshwater input, the river inputs.
I guess a related question, Dave, is that, well, you define the salt front, when salinity is about 1, but when you get to very low salinity, like 0.25, and the chloride, the salt it washed from the road, also reaching that level. What's driving that salt transport? Is that still an intrusion problem, or it could be some other process that affecting that distribution, salt distribution?
Yeah, it's a very good question. I think that was part of that. Those types of questions what sparked this whole webinar series, just because you really are at this interface between physical oceanographers who stop caring when you get below 1 PSU and hydrologists who tend not to think about salt that much in general. And that's a broad brush. There's some who think about it quite a lot. And so certainly as you get to lower and lower salt concentrations, the composition of the ions matters. And then I think also the transport processes are going to change. When you have, in most sort of estuaries, the salinity gradient, the horizontal salinity gradient is really important for driving horizontal transport. As you get to really low salt concentrations, that horizontal salinity gradient gets really weak. And so something else is likely to take over as being the dominant, whether it be tidal processes, whether it be episodic inputs, and so forth. So I think that is a really good question. I think that's, it's not even something we're particularly well suited to measure. I mean, you can see it in the sense of the way Bob and I talk about salinity in PSU, and then Randy talks about it in terms of chloride levels. And so it's coming at the same problem from 2 different directions.
So there's another question from Steve. Sorry, I can't. For long-term depths, the sediment load may cause the bed elevation to keep up with sea level rise, as Bob showed. Dave has also done work on upstream dam effect and sediment trapping. Are the sediment now reaching the estuary the right same composition for bed aggregation, I guess? What's the future of sediment load? This is for both Bob and Dave, I guess. Or Dave, maybe.
Yeah, I can take this one. It's a good question. I think it's, again, sort of thinking even not just about the Hudson, but thinking about other systems, because the variability in sediment load from the system really depends on how the watershed's managed. In the Hudson, so some colleagues, Brian Yellen and John Woodruff at UMass, did a lot of nice work looking at that exactly. How much sediment is trapped behind dams? Are the dams in the Hudson? There's more than 200 dams in the Hudson, just in the lower Hudson below the tidal inputs. But they're mostly really small. They mostly were like old mill dams, which were built associated with farming practices. And so they mostly filled up a long time ago. And so they're bypassing sediment. And so the actual input, for the most part, the impact of dams on the sediment supply in this particular system is pretty minimal. You compare that with some of the West Coast systems, where these really big dams, which are still trapping a lot of sediment, then both sort of the continued trapping and then potential dam removal can have really big impacts on the sediment load, and then potentially the likelihood that an estuary will either keep up with sea level rise as far as an infilling rate or not. And I guess that's in general sort of in a system with sufficient sediment supply. We tend to think of the hydrodynamics of keeping an equilibrium depth for the channel, in the sense of if it gets deeper, then the currents slow down and the sediment fills in. If it gets shallower, the currents speed up and the erosion makes it deeper. So there is that natural feedback to get to an equilibrium depth. But if there's not sufficient sediment supply, then that might not be the case.
And then Bob wants to chime in, I guess.
No, not only to that, I was going to ask Randy a question. Maybe he already said this. And I missed it. But what did you guys do what did you guys do in 1995 or during these salt intrusions? You treat the water, or you ship in water from elsewhere? And if you ship in, well, go ahead. Yeah, answer that.
We have to treat our water. We don't have a choice. It's the only supply for the area. So fortunately, it hasn't come in and lasted that long that it's been something that's going to be addressed.
Oh, so you just don't pump when it's that salty, and you just have a reservoir basically.
We have a tank that can hold about 8 hours. So we can shut down for 8 hours and pump around things if we want to. We could try that. But you know, the worst was, like I said, 2004 when we hit that 230 milligrams per liter chloride that I've seen. But I've been here since 97. So.
The guy who was there in 95 quit probably.
They didn't have a guy for 95 sort of thing. In 97, the city and town got
out of here
on the plant.
I have a question for Randy. When is water demand the highest? Is it also when you have concerns over like salt intrusion?
The highest is in the summertime. Yeah. And it's more flat than a lot of regions I've been in, but it is higher in the summertime. We just put out what we can, we just put out what the customers want, and that's how it goes. So I haven't seen anything. The one chart that tells it all is the Green Island flow. Is the flow is not very big up there. We're going to get salt.
Yeah.
So it looks like we have a raised hand from the audience. Alex Warner-Devine, ask a question.
You want to talk? We could.
I think I mean.
Can you hear me?
Yes.
Thanks. This was too long to write in the things. My question is, I guess, for Bob about upstream salt flux, and just thinking, along the lines of this idea that you're focused on less than 1 PSU, and the question of classifying that salt flux, and whether the scaling that you presented, that's all in terms of, or that is framed around DSDX, is likely to apply if, in the low flow sections that we saw, there are strong gradients further downstream and stratification further downstream sometimes, but it's pretty well mixed, and the gradient is much lower, especially up less than 1 PSU. And so I'm wondering if you're thinking about how you'd adjust that model for predicting salt flux at the upper extremes of the salt intrusion.
Yeah, that's a very good question, Alex. And it's sort of, I kind of alluded to that in my third point of my conclusion with caveats. And yeah, I mean, the thing is that, as I said, the thing that drives salt downstream is river flow, which is the river discharge times the salinity. And so as you get to the half a PSU, quarter PSU, the river has a hard time pushing salt downstream because there isn't much salt to do that. And so, as you should notice, and if you look at some of the figures, like some of the stuff in Melissa Bowen's work, you see this section, and you see this a lot of estuaries too. Like the last couple isohalines, they kind of spread. They kind of, they're much more, like you said, DSDX naturally decreases. So I suspect, as you were alluding to, that yes, that those scalings probably don't work in that last bit of a PSU, and it's probably tidal dispersion becomes much more important, trapping and all that kind of stuff. And in fact, like I said, I mean, maybe Dave should pipe in here too, because I think that like a lot of the sort of the Q to the 1/3 in the estuary was like up to the 5 PSU isohaline, and you definitely see, and the thing is that a lot of that intrusion is sort of like these fronts that form during spring tides and then work their way upstream, as almost like gravity currents. And then, but upstream of that, you see some other like more diffuse salinity gradient. So yeah, I think those scalings probably not going to work in the last couple PSU, but I think where that last couple PSU start is going to probably be influenced by things further downstream. But I think this is what Selma's going to tell us about next year, right? When she comes to Rutgers and gives a seminar.
Hope so.
Which doesn't know about yet, but Dave and I are working on this in Delaware too. So it's another I think it's an interesting topic.
Great, thanks. I'm looking forward to those results, Salman.
So there's a question from Suja Kojo, who is also co-PI of this project. He has a question for Stuart. Can the salinity level influence zooplankton in Hudson like in the lakes? Are zooplankton not as important in Hudson?
Remember to unmute myself. So yeah, the zooplankton are very important for the young fishes. You know, they come out of their yolk sacs, give up their yolk sacs, and they turn to zooplankton for their diet. And the composition of that zooplankton is very different. There are a lot of cladocerans up here and more copepod dominated fauna further south. And so those are going to change. You know, fish are relatively smart. And so I think they'll figure out what there is for them to eat and get by. I'm not 100% convinced they're food limited in type, that you know, a small particle that they can digest, one is probably about as good as the next. Size is very important. The bigger the better, obviously from their point of view. And so there may be some differences as the zooplankton composition changes, but I think the fishes will probably figure it out fairly quickly. I mean, time will tell. Most of our fish stocks have such large other problems that having enough to eat is perhaps not the most critical. Hi, Sujay.
So I have a question for Stuart, as long as you're on the platform right now. So a lot of times systems you think about, I think about anyway, whether it be marshes, for example, or your SAB or even fish, as the whole system progresses landward, you expect the ecosystems also progress landward. Do you think that's, are there limitations on that in the Hudson, or is that what you expect to happen there as well?
Yeah, so this is all tied up in this inundation issue. And in most cases, when sea level rises, if the topography allows, and that's going to be the big thing, if the topography allows, these things transgress inland. The problem in the Hudson is the topography, for the most part, doesn't allow. They're very steep slopes. It's an old glacially carved valley. And so the inherent topography doesn't give these marshes much room to move. And then on top of that, there's a bunch of human infrastructure that's not going to give them a lot of room to move. For the few cases where they can, a couple of the conservation organizations have been very good about saying, you know, we really need to protect these lands and going out and getting those things protected so that 50 years from now, the marshes will have a place to move from. But the total area where that's going to be possible is small relative to the total number of marshes. So we need to be thinking about other things, and you know, artificial sediment augmentation, I'm afraid is going to have to be on the list, although it's not a tremendously attractive option.
But what about in the subtidal, where things are influenced by the salinity intrusion, for example?
So again, the SAV can probably move laterally just as things get deeper. I think, you know, if salinity gets to high enough levels, we're going to chop off the southern end of where the submersive aquatic vegetation is right now. And the likely colonizers for that are a long way away. You know, it's not as though they don't exist, but they're a long way away. So in the case of the marshes, there are existing marshes where the sort of brackish tolerant species are already present. And it's easy to see that they wouldn't have too hard a time just moving along as the salt intrudes. For the SAV, you know, they got a bit of a trip in front of them. And so I think it's going to be at least slower, if not very difficult.
A couple more minutes before 2:30. Are there any more questions from the audience? You can raise your hand, or there's Phil Jasinski. See if you can talk now.
Yeah.
Hi, Phil Dazinski from Philadelphia Water. One of the things that we noticed at PWD when There is some dry periods where the salt front does move up, but even the ones that really don't get that close to the very lower boundary of Philadelphia, there's the impact of that lower the oceanward salinity coming up is seen at specific conductance stations, fairly maybe like all the way up to Ben Franklin Bridge, which is near at the like halfway through the area of Philadelphia. So there, the mechanism might not be as clear of what that transport is, but there's some effect that is seen that I suspect that I don't know if this is possible. We certainly don't have a lot of time to talk about it, but just the fact that the flow has been diminished quite a bit during this dry period, wouldn't that have a barotropic effect by reducing that barotropic effect from the upstream water being depleted? I mean, could that cause some transport just from that effect?
Yeah, that's an interesting point. Well, go ahead, Bob. You gonna say something?
No, you take it first.
Well, I was going to say, I mean, certainly in many tidal rivers, we know that the amplitude of the tide depends on the river flow, and as the river flow goes down, the tides are essentially have less opposing them to travel upstream. So, if, for example, you think that tidal dispersion is playing a big role in that low salinity part of the transport, then the tides would get bigger during low flow period than during high flow period. So you could imagine that could be a contributing factor to increasing the landward transport in that low oligohaline zone.
And I just want to say that Phil certainly thinks that tides are important driving salt flux up there, because he just finished his PhD dissertation with me and showed that also in the upper reaches of the Delaware, which I should have said before. So.
Okay, well, it's 2:30. Thanks to everyone who joined the webinar. Thanks to all the panelists who contributed. Like I said, stay tuned for more emails on this topic. We hope to have another one sometime in the early part of next year, likely looking at the Mississippi River, which is another area of big interest for this topic. So thanks to everyone, and take care. Happy holidays.
Bye, everybody.
Bye.